Starting with the reporter, I think probably most helpful would be if we can go through this rubric. So most of you guys have probably seen this already, but we'll go through a little bit more, I guess, in depth. All of you guys, your goal should be trying to get as high down here as possible. So I'm just going to be going down basically one row. So starting with your report, you can get a maximum of 7 points. So for your phenomenon explanation, basically this is like your initial observations. But it's important that in your initial observations, you're not actually just observing the phenomenon. It's also about trying to hint at some like the physics concepts that are actually behind that phenomenon. I'll show you guys an example of this later. But the point is not just to show a video, but use that video to show some important physics concept. Moving on to your theory or model. A few things to note here. It has to be correct, obviously. It has to be as detailed as possible. And as Professor Xu mentioned earlier, complexity is good here, but you also still need to be able to draw conclusions from this with your experiments. So if your theory is some like unsolvable partial differential equation that you can't test in your experiments at all, it's basically worthless, right? So you need to be careful that you don't make your theory so complex that you can't actually test to make sure that your theory is actually correct. Okay, relevant experiments. So like I mentioned earlier, this has to be a way to test your theory. And ideally, you shouldn't be using too advanced of a setup. Nothing in IYPT really requires you to use very expensive equipment for the most part. So basically, it should be a clever way to try and get data that will prove whether or not your theory is correct. And you need to have a significant amount so that you have some kind of statistical significance. Yeah. And next, you have the comparison between your theory and experiment. So here, it's important that you don't do just some qualitative analysis. So at TYPT, a lot of teams like to plot the two lines next to each other and say, look, they fit. That's not enough for IYPT if you just say that they look somewhat similar. So for example, a good way to do this is if you fit some constants, and then you check to see if that constant has some kind of physical meaning. And if that constant does, then you know that your theory matches. But if it doesn't, then your theory doesn't match, right? Yeah, okay. Own contribution. So for some topics, especially like looping pendulum this year, there's a lot of already well-established literature. And so make sure that you guys do more than just summarize what has already been done in the past. Because these should be your own experiments for the most part. Even if you borrow someone else's theory, try and improve upon it by maybe adding in some more correction factors that weren't considered in that paper's theory. Right, so I think this is especially a problem for you if you guys do choose to do that. Try and add your own touch to that experiment so that you're not just repeating what's already been done online. Okay, and task fulfillment. This is whether or not you actually answered the problem statement. And for 7 points, this is really difficult to do, but if you can go even beyond what the problem statement asks for, and maybe test stuff that isn't actually even inside the scope of the problem statement. But remember, first you need to answer the problem statement. And then you can go and try and see if you can test stuff above and beyond the problem statement what it asks for. And the last one, science communication. And this is related to just technique of your report, basically. And she'll go into more detail on what exactly your technique should be like. But basically what this means is your presentation needs to be clear and well organized, which means that basically you should use less math if you can, and more physics, right? So you want these concepts to be easily understandable, so that after 12 minutes, you don't confuse everyone, but the best case scenario is that they can understand everything that you went through. If you guys have any questions, feel free to ask. Am I going too fast? Okay, cool. So the next part is during the discussion. Obviously, there's not too much that you need to do as a reporter because the discussion should be led by the opponent first and foremost. So relevant arguments and responses, this is pretty self-explanatory. So basically, you just need to demonstrate during the discussion that you can defend your theory and your experimental data and show that you can also understand the topic. For reporter's conduct, this one is also fairly easy to do. Basically, don't waste the opponent's time by trying to evade questions. And if you do try to avoid questions, it's usually very obvious if you do. So whatever you do, do not actually, or don't try to waste the opponent's time if you can. And the last thing to note here is the answers to the jury, opponent, and reviewer's questions. So you notice the scale actually starts at 0. The highest you can get is 0 points, and you can actually lose points if you do stuff wrong. So what this means is two things. One, if you do super well, you're not actually going to get any extra points. So it's okay if you just do kind of average in the answer. But the other thing is, you can't like start making up BS examples or BS answers, or you can't, I don't know, try to avoid those questions, because if you do, then the jury might want to take off points in this section. So keep in mind two things. Your answers need to be very concise, and your answers also can't be incorrect, obviously. Okay. So this is, you guys can't really see that. We'll send this later. It's not super crucial for you guys to know this now, but basically this is kind of like a suggested plan for how the team should behave during the competition. And if you are selected for IYPT, it's important that you guys have some kind of plan for your own team. And obviously this depends on your team's dynamic, right? So last year, for example, I'm a really fast typer. So even though we had one person for that round assigned to using that computer, I would always end up helping with the typing, right? So it's important that you guys also adapt this to your team. But the basic idea is that you have a performer, a supporter, a messenger, a computer, and a backup person. So the computer and backup are in charge of the PowerPoint, and they control both the computer that's currently being used and the backup computer. And then you have the messenger that helps with communication between all these different team members. You have the supporter, who's basically like the second performer. So this supporter is usually the next most prepared person during the competition for that topic, next to the performer. And basically what they're doing is giving the performer the support that they need. So feedback on how they just did during the report, for example, or maybe passing them notes to help them answer questions from the opponent or answer questions from the jury. So that's the role of the supporter. And again, it's not super crucial for you guys to know now, but you guys, if you are selected for the team, will need to prepare some kind of plan for what the different team members will be doing during the actual report.
Okay, so now I'd like to talk about being the reporter. What should you guys prepare? And now we're going to have the introduction of what a reporter should demonstrate on their report. So here's a brief structure of what the reporter should do. First of all, the problem statement, the outline, the observation, the setup, theory, and possible the relevant analyses, data, discussion, and final conclusion. And I will explain it relatively. In following minutes, I will tell you guys what you have to do for preparing these pages. So for the first 3 pages, they are pretty simple but crucial for your report. Since it is possible the first time for your juries to contact with the problem statement, it is our responsibility to let the juries understand what the phenomena would look like and what's the point that we should investigate on. So for the problem statement, it's very clear that we just have to copy the full problem statement on it, and we should highlight the key words on the problem statement. And by doing so, we can make the complex problem statement be more clear and easy to understand. And for me, after a problem statement, I like to point out some main focus to that the jurors and your opponent understand what you're going to investigate and how you comprehend the whole problem. And as for the outline, the function of this page is pretty simple too. And you just want to use this to make your opponent and your jury grasp your PowerPoint more easily. And with this page, you can expect that they are going to do in the following pages. And for the observation, actually I think that the observation is much more important than the problem statement. Sorry, only from looking at the problem statement. Actually, I think most of the people cannot really understand what the problem statement is actually talking about. But from maybe the observation video, the observation picture, or the animation, we can clearly see that what the phenomena would look like and what were the dynamics in the phenomena. And following, we will show you, not following, soon after, we will show a kind of example about Team Singapore, and they did really excellent in the observation and be aware of it. Okay, and now I would like to talk about the demonstration of the theory. since that when I'm watching you guys performing in these years TYPT, there are a lot of mistakes in performing your in your theory. I know that a lot of you guys have really good mathematical skills and you have very good physics skill of calculation, but the complex and detailed calculation is not necessary to put on your slides. Because it is really impossible for your opponent and jury to grasp what you are actually computing while about 30 seconds. So never put this kind of theory on your graph. You can put it in your backup page, but not on your theory slide. And what we want is the theory that only with the simple physics inside of it. Just like this, maybe not a lot of formula, but about clearly understand what you're going to talk about. And so the theory that I just talked about, and about the relevant analysis, it's not an essential part for your report, but if you did some relevant measurement for your experiment, that will be great. For example, like these years looping pendulum, I saw a lot of your team did measure the friction coefficient of it. However, a lot of them in TYPT do not really demonstrate how they measure all of their measurements. And it is really a pity that you don't show it to everyone. So if you did the relevant analysis, please show it. And in this part, you have to show your measurement setup, your analysis, and your results, which is relevant to your measurement. And about the experimental data, I will put some time explaining how to draw a right and qualified graph. And I hope that after we teach you guys how to draw the right graph, you will have the beautiful graph in your progress report and while you're discussing with the professor, because the wrongly drawn graph will waste a lot of time when. So now I will show 3 miserable graphs that I saw in TYPT. A lot of you guys did these 3 kind of graphs, sorry. And the first one is the screenshots, and it's really bad to screenshot any kind of graph that is from the software, no matter the tracking or the Audacity. The graph drawn by these software are usually not clear enough, and using the screenshot shows that you have no sincerity on analyzing your data, and usually the data that you can screenshot are the preliminary data, which we don't want you guys to perform in your PPT. And the second one is the most commonly seen graph in TYPT. I can tell what this kind of graph is not really graph. It didn't have it didn't have the label for the x-axis and the y-axis, and it didn't have the units, and it didn't have the arrow bar. The graph that without the label is just not the graph, because nobody can understand what you are demonstrating about. And the graph without arrow bar means like your data point is not really reliable, since you only did your experiment one time, and we cannot sure that if the data point is accurate enough. So please, add your arrow bar on your graph. And the third one looks a little bit better than the previous 2. However, it has a serious problem that it drew the line between 2 data points. Drew the line between 2 data points means that you predict the data between 2 data points will be exactly on the line you drew, and that is impossible for the data point between 2 data will be on the line. So please don't draw the line between 2 data points. And so this 3 kind of graph is not available. So what is the graph that we can draw on your graph? It's the graph that the guy likes. So first of all, we check that these graphs have every element that we talked about. First of all, you have the title, and you have the axis, and you have the correct label, and you have the units. And for the units, please have the blank between the label and the units. And you have the arrow bar and the legend to tell everybody what is each item be. And to draw this kind of graph, we will not use a software such as Excel or Tracker or something else. We usually use Origin to draw this kind of picture. So here I'll have the brief introduction about how to use the Origin to draw a qualified graph. So how can I move this to? Oh yes. Okay, so B is the software Origin, and we will look. You have several. Like we will have the book here, and we can draw the graph. And now I'll cancel the graph and tell you guys how to draw the qualified graph. And actually, there are a lot of functions from in these software, but today I will just talk about how to draw a graph. And finally, you can develop like fitting FFT from these great software. So first of all, you need to have your data point here in your book, and you can create book here, okay? And you can just type your label here. For the long name, the first one, I think that the x-axis is the time of it, and the y-axis will be the velocity. And you can just type the unit here, and the Origin will draw it for you. So you don't have to aware that you don't have to do the units. And about this, we need to add the arrow bar for this graph. So how to add the arrow bar? You just need to press here and add new column. Then you will have the new column. And for the new column, we have to choose the property of its property. Where is the property? Then here's a lot of things that you can choose. And for plot designation, you can choose arrow here. So if you choose the arrow, and you will be your arrow bar on your graph. So now what I have is our x-axis, our y-axis, and our y-arrow, okay? So with this three data, we can draw our graph. So just mark this three, and here are the things. Usually we plot scatter line. So here will be our graph, but this graph is actually not a qualified graph because it's not really beautiful. So let's start with the axis. We don't like the axis look like this. We want the tick big inside and the axis be thicker, and we need the we don't want the graph look like this. So still you process and choose property. Property is really a good thing that you can change everything in it. Okay, so change the tick out into in. Then no matter the major one or the minor one. And the thickness, usually we use 3 for our graph. Okay, and we can choose other axes together. So show the axis and the tick, and the thickness 3, and in is pretty well. In the top, show the ticks. And for the top, we have to type your title here. And for your every graph, we should have the title, because the title may make the opponent and the jury grasp what you are demonstrating quickly. So the title, the velocity, okay, versus time. And okay, still change the axis into 30, and the bottom one. And the tick's always in. Do you guys remember what I did? If you forgot these time, you can ask me, and in any time, and I can help you to draw the right graph then, okay? Now we have the better graph here. the legend inside of the graph. Okay, so now we have the label, we will have the units, we have the title, we have the right axis and the arrow bar. So this will be the qualified graph, and I hope that you guys can use Origin to draw your every graph. And in the following discussion, in your progress report, you can show the qualified graph. So now let's go back to our PowerPoint. So next, I will talk about some formats. Well, now I would like to talk about the format mistake in your report. And these are actually the minor mistake, which is not as important as the previous one. But nevertheless, correcting these mistakes may help your PowerPoint be more clear. So for starter, sorry, and for the color, the color which are available to put on your report are black, blue, red, and green. Only these four colors, since that we are competing in the physical tournament, not arts competition. So just use the color that can make your PowerPoint be clear, and never use a color such as sky blue, pink, bright green, or others. It will not help your PowerPoints. And secondary, about the type of words. In one PPT, please only use one type of word. Do not change your words all the time. And no artistic font like these three. I know that these three are really beautiful, but it's useless in your PowerPoint. It will not help your physics be better. So do not use these beautiful words. And about your size of the word, we cannot expect that our projector is pretty well. So use the bigger words will make your PowerPoint be more clear. And also, some of the professors have really poor eyesight. So please use the size over 50 for the title, and for the page number, the size have to be over 36. And for other details in your graph, please choose the size over 44 in PowerPoint. Okay, so now we will see a brief example for the video.
Yeah, so we're just going to watch a short clip from, this is last year's IYPT finals. Singapore is reporting on azimuthal radial pendulum. Some of you guys might already know that problem. So as you guys know, Singapore has won a lot of gold medals at IYPT, and the reason for this is because, I mean, their reports are actually just fantastic. And they're kind of like the gold standard for this competition. So if you guys do need inspiration, I highly suggest that you guys go on YouTube and try and look for some more of these YouTube videos online, especially from Team Singapore, because those will definitely be pretty good. And I want you guys to also keep in mind all the things that Junior here just went over, and see if they make any of these mistakes that she mentioned, which they shouldn't, obviously. And there's one more thing that I want you guys to notice from this report, and that's regarding their observation video. I'll talk about that a little bit later. Let's just watch it first.
Ready? May I begin? Sure, please start. Good afternoon, judges. I'm Fu Xinghong from Team Singapore, and today I'll be presenting on problem number 11, azimuthal radial pendulum. The problem statement asks us to investigate the spontaneous conversion between radial and azimuthal oscillations in the following system, where the motion of the pendulum bob is governed by the length of the elastic beam, the length of the string, the mass of the pendulum bob, the angle of release, and the angle of the supporting string. Here is an overview of what I'll be covering for today. We will begin with an introduction into our experimental setup and key observations. Then, we'll move on to a qualitative explanation and a quantitative model of the phenomenon. First, we begin with an introduction into our experimental setup. The elastic beam with a pendulum bob attached at its end is shown in the diagram above, with the top string to avoid vertical deflections as stated in the problem statement. To ensure a controlled release of the pendulum bob, we employ a robotic release mechanism. Upon the release of the pendulum bob is then trapped with a high-speed camera mounted below the experimental setup, and the motion paths of the tip of the elastic beam and the pendulum bob are then tracked using computational pixel counting techniques. We calibrate our system for parallax errors and obtain the following grid in the camera's plane of view. Then, using the length constraint of the string, we are able to solve for the full 3D position of the ball in the left frame. Moving on to preliminary observations, we begin by defining two frequencies for the radial and the azimuthal modes respectively. These are parallel and perpendicular to the rod as stated in the problem statement. At the frequency ratios as shown above, we observe no clear occurrence of the phenomenon. However, a slight adjustment of the frequency ratio allows us to observe a distinct onset of the phenomenon. This hints at the possibility of resonance in this system, which is due to its characteristic frequency ratio matching in resonance systems. With that, we will now move on to qualitatively explain our observations. It is important to note that when the pendulum board is set into a perfectly radial motion, there will be no conversion to azimuthal motion observed. For the next section, it will be helpful to analyze the forces from the bottom view to see what happens to the system when the system is non-ideal. Let's first analyze the first pendulum half cycle with an introduction of a small disturbance in the presence of a small azimuthal angle. When the beam deflects towards the left, the pendulum board swings back and pulls further on the beam, deflecting it further left. Then, as the beam swings back towards its equilibrium position, the pendulum board swings forward and as a result, deflects the rod in the direction of its motion, inputting energy in the rod's motion. In the second half cycle, the same process applies as the beam deflects towards the right and the pendulum transfers its energy to the rod by the process that I previously discussed. To maximize this energy transfer process, the string tension has to be perfectly in phase with the beam oscillations, which translate to the radial mode, in this case, having twice the frequency of the azimuthal mode. In this scenario, the radial oscillations will decay and the azimuthal oscillations will grow exponentially. Moving on to analyze the full energy transfer mechanism, the first phase is what we have previously discussed. As the rod is deflected azimuthally by the pendulum board, it then pulls on the pendulum board in the azimuthal direction, and the board then reaches maximum deflection as we can see in the following video. However, in this azimuthal motion, there still exists a small component of the string tension which deflects the beam in the radial direction. We also note that there's a presence of the curved path traced out by the tip of the cantilever beam, and this swings the pendulum board in the radial direction. In converting the azimuthal oscillations into a radial one, a process reverse that of phase 1 is used. It is important to note now that the string tension opposes the rod motion. This extracts energy out of the rod, and this cycle repeats, and the whole system is damped out by air resistance. Now, let us move on to a quantitative model. We start with the equations of motion, followed by a characterization, and then experimental verification. We consider our elastic rod as an Euler-Bernoulli beam undergoing deflection. We define S as a coordinate along the beam, U and V as the displacements in the X and the Y directions respectively. With that, we formulate the following Lagrangian, which comprises the kinetic energy and potential energy term. Here, psi denotes the slope curvature, which is illustrated in the diagram above. However, to impose the inaccessibility constraint of the beam, we write the Lagrange multiplier, which can be physically interpreted as the force required to maintain the inaccessibility constraint. To account for the effects of viscous damping, we include the work done by non-conservative forces, and we are able to apply the extended Hamiltonian principle. We obtain the following equations governing the motion of the cantilever. The inertial, damping, and constraint forces are taken into account. The nonlinear elastic force in this equation is obtained by extending the slope curvature psi to fourth order to account for large deflection in the cantilever beam. We also re-obtain the inaccessibility constraint in the beam. To obtain the boundary conditions of the above equations describing the elastic rod, we resolve tensions in the top and the bottom strings respectively in the xy plane. Here, we write a force balance in the radial and azimuthal directions respectively. We formulate the last equation which governs the force balance in the vertical direction. To obtain the tension in the bottom string T1, we analyze the free body diagram on the pendulum board And right, Newton's second law in the accelerating frame of the cantilever tip. In this case, we are able to impose a length constraint which governs the length constraint of the string connecting the tip of the cantilever to the pendulum ball. This completes our equations of motion. Now, we move on to characterize our system. To obtain the Young's modulus and the damping constant of the beam, we track the angular frequency and amplitude decay, respectively, with an added mass at the beam tip. This graph gives us the following two graphs which we have plotted. To account for the effects of the top string on the oscillations, we write the equations of motion as follows, where lambda represents the in-plane component of the tension in the top string. We write the following boundary conditions at the fixed and the free end of the cantilever beam. The last equation is written with a force balance at the tip of the cantilever. The last term in this equation represents the effect of viscous damping, which can be characterized by solving these equations numerically and filling the decay envelope. Doing so, we are able to obtain the following characterized values for our beam rigidity and damping constant. We input these values into our theoretical simulation. To characterize the effects of damping on the pendulum, we track the amplitude decay of the pendulum oscillations. To account for the finite radius of the bob, we write the equation of motion for the physical pendulum and once again fit the decay envelope to obtain the following value for viscous damping constant. Now, moving on to experimental verification. We start by plotting a critical position time graph for the pendulum where we can observe a clear transition between radial and azimuthal oscillations with an excellent experimental agreement. The amplitude of the peaks decrease over time due to damping. The beat frequency also decreased as a result of damping. If we start the pendulum off from a pure azimuthal mode instead of a pure radial one, the only effect is a shift in the initial condition in the same position time graph as we have verified experimentally. To visualize the energy transfer in the system, we first define the total kinetic and potential energies in the azimuthal and radial modes respectively. We plot that against time and we see a total energy loss due to damping and a clear energy transfer between these two modes. This is also experimentally verified. We conduct a Fourier sweep of the displacement time graphs and observe that the frequency of the radial oscillations is equal to that of the frequency of the pendulum oscillations. This is twice that of the azimuthal oscillations. It is important to note now that the azimuthal system oscillates at half the driving frequency and not its central frequency. Zooming into the FFT of the azimuthal position, we see the presence of high-order harmonic peaks, which are due to the beam being driven such that it oscillates at a superposition of multiple modes. This is also theoretically predicted. As we vary the mass of the pendulum bob, we note that the amplitude of oscillations increase due to increasing total energy in the system. The beat frequency also increases as a result of increasing rate of energy transfer in this system. To investigate the effect of the initial angle of release, we first define the maximum amplitude Ymax. Plotting that against the initial angle, theta, we see the following trend. As we increase the angle of release, the increasing total energy in the system results in a larger azimuthal deflection. We also note the presence of a cut-off angle required for resonance to occur, where below which there will be no conversion from radial to azimuthal oscillations. We can define another property of this graph, which is the period of the first beat. We plot that against the initial angle of release, and we see a decreasing trend. Analyzing two cases of the following two angles, we see that increasing the angle of release will increase the rate of energy transfer in the system, and as a result, maximum deflection will be reached more quickly. The asymptote of this graph also approaches the critical angle of release. Now, we vary the length of the string, and we see the following trend as we see a plateau near the point of peak resonance with high amplitude and high frequency oscillations. These three regions correspond to the three frequency ratios that were presented in our preliminary observations, which proves that frequency ratio matching is required for the phenomenon to be observed. We also observe that the ideal frequency ratio for fast and obvious conversion is around 2. Now, let us discuss the onset of resonance. We can obtain the following phase plot for our system, plotting the frequency ratio against initial angle of release. Parametric resonance is observed in the green region. The width of the green region increases with increasing angle of release as the magnitude of the parametric driving force increases. We also note several interesting effects of damping on this graph. We note that there's a critical angle of release required for the magnitude of the parametric driving force to to balance the rate of energy extraction due to damping in this system. We also note that the bifurcation frequency lies around 2, which matches our preliminary observations. So in conclusion, we started off with a qualitative explanation of the phenomenon where energy transfer mechanism relies on parametric resonance in this system. Our quantitative model writes the equations of motion for the cantilever beam and the pendulum bob. Effects of air drag has also been considered. We are able to experimentally verify the dynamic motion half of the pendulum bob and investigate the effect of varying parameters of the motion of the bob and the oscillation. The onset of resonance has also been investigated. Here are references. Thank you. Thank you very much. Questions from you?
So let's just go category by category and then just shout out what scores you would give them. So for the first category, phenomenon explanation, what do you guys think? Anyone?
So 1, 2, 3, raise your hand with your answer.
Okay. Who would give them a, I'll start at 3. Who would give them a 3? 4? 5? 6? Okay. I think in this case that's actually pretty correct because, as I mentioned earlier, they talk about resonance very early on. And in their initial observations, they kind of explain that resonance that they see, and later on they verify it with their mathematical theory. And I think that's something really great that they did here, is that when they do those initial observations, instead of starting to go straight into the math, they did a lot of qualitative analysis with that resonance. So I think for that reason, yes, it is definitely deep and comprehensible, and it definitely does show some physical insight. Okay, for the theory or model, any 4s? 5? Okay, 6? Interesting. Okay. Do you guys want to share why you guys gave a 5? I don't think you're necessarily wrong if you have a reason. Okay, I guess that's okay. The difference between the theory, I think I'd probably give them 6 for this one as well. And the reason being, their theory includes a lot of smaller, I guess, details that you might not initially consider. For example, some people might have modeled the horizontal rod simply as a spring that goes linearly, but clearly they did not do that. They also take into account the fact that the upper string also is a factor inside of their theory. And all of these things, for some teams that don't have as detailed theory, they're kind of neglected or assumed that they aren't as important. And so, like Professor Xu pointed out earlier, having that complexity by not making those assumptions first off can actually improve your theory by quite a bit. Okay, and regarding relevant experiments, any 4s? 5? Okay, and 6? Okay, interesting. So, in this case, the 6 is the majority. Do you guys want to explain why you guys think it is deserving of a 6? Okay. I guess the small nitpick here, maybe why you give them a 5 instead of a 6, is because of the fact that they don't actually talk very in-depth regarding their experimental methods. Now, the reason being, they have so much other material to cover. I'm sure they have it in their backup slides and not in their actual report. And so for that reason, maybe it's not as reproducible if you've only listened to this report. So maybe that's why you give them a 5. But I think that they did a good job of explaining the results. And you guys noticed that they took very different approaches. So a lot of you guys would have done is showing the period versus the effect of some parameters like the angle. But in addition to that, you also saw that they showed the graphs of the potential energy versus time, right? And all of these other experiments, these different ways of analyzing that data, and at the very end when they showed that phase diagram as well, all these different ways of analyzing the data in addition to having those experiments, makes your experimental data a lot more strong. Yeah, so this kind of ties into the next section, which is comparison between theory and experiment. What do you guys think? 5 or 6? 4, 5, or 6? Okay, 5s, raise your hand. And 6s? Okay. I think this is also kind of in a gray area as well, between 5 or 6. All of this is kind of subjective though. So, like I mentioned earlier, they took many different approaches to analyzing their experiments. And when they mentioned the new ways of analyzing their experiments, they always said, we verified this experimentally. And so, what you see is that for every part of their theory, for all of the assumptions and for all of the constants, like the drag coefficients, all that kind of stuff, they did experiments to make sure that it matches with their theory as well. And so that's something that they were really strong about. Okay, own contribution. I think this one's a little bit hard to grade, but anyways. Anyone give a 5? 6? Okay. Yeah, so in this case, I don't think it's really experimental or theoretical. They did actually do, I think, quite a bit of both. If you saw on that final slide, that stuff is not just theoretical, I'm pretty sure. They do experiments to actually verify that kind of stuff. Even if they don't show all of their experiments, the fact that they have all that experimental data to match and back up their theory is what makes this report so strong. And even though you guys won't get to see the discussion, you guys can look at it later. But Singapore always prepares a lot of backup slides, and you'll notice during the discussion, whenever they get challenged on any part of the presentation, they always have a lot of experimental data, and they always have a lot of backup slides to kind of refute whatever concerns the opponent might have. Okay, and task fulfillment. What would you guys give? 5s, anyone? 6? Okay, yeah, I think I agree here. But Singapore always does that. It might seem like it's not really achievable for you guys, and maybe it's not achievable in the 5 weeks before tuition. But at the very least, you guys can do the analysis of the data that they did, right? That kind of stuff doesn't require you to do very time-consuming experiments, but it does, it really makes your report a lot stronger than what you might bring to a 2IPT competition.